Humanity's farthest messengers are about to fall silent, but a plan is already taking shape to send a successor. For nearly 50 years, the Voyager probes have been our eyes and ears in the void, but their 1970s technology is fading. Now scientists are designing a true interstellar explorer, a robotic probe built to fly faster, see clearer and journey deeper into the cosmic ocean than ever before. This is the story of the mission to build Voyager's heir. Let's explore this together. The original Voyager achievement. Ever wonder how two probes from the 1970s became the greatest explorers in human history? The answer is a mix of brilliant engineering and perfect timing. Managed by the Jet Propulsion Laboratory, Voyager 1 and Voyager 2 launched in 1977, taking advantage of a rare planetary alignment that happens only once every 175 years. This Grand Tour alignment allowed them to use gravity assists, slingshotting from one giant planet to the next. Under the guidance of scientists like the legendary project scientist Ed Stone, who served for 50 years, the discoveries were staggering. We saw active volcanoes spewing sulfur on Jupiter's moon Io, confirming 9 active eruptions and making it the most geologically active object in the solar system. We discovered the icy geysers of Neptune's moon Triton, a world so cold it spews nitrogen frost. These missions completely rewrote planetary science textbooks, all accomplished with custom-built computers that had just 69.63 kilobytes of memory, less than 1/1,000,000th of a single photo taken by a modern smartphone. They transformed our view of the outer planets from fuzzy telescope images into a detailed family portrait, revealing worlds more dynamic and complex than anyone had ever imagined. It was a mission of firsts, providing the data that forms the foundation of modern planetary science. The journey into interstellar space. But their planetary tour was just the first act. Once their primary mission ended in 1989 after the Neptune flyby, the Voyagers just kept going, beginning the Voyager Interstellar mission. Powered by their radioisotope thermoelectric generators, they traveled onward toward the boundary of our solar system. That boundary is the heliopause, the edge of the vast magnetic bubble our sun creates called the heliosphere. In August 2012, Voyager 1 finally crossed that boundary at a distance of 121 astronomical units, or 11 billion miles from the sun. The moment was confirmed by Don Gurnett and his team at the University of Iowa when the Plasma Wave System instrument detected the vibration of dense interstellar plasma, a 40-fold increase in density that sounded like a sudden tone in the data. It was the sound of leaving home. Voyager 2, which took a different route past Uranus and Neptune, followed in November 2018, crossing at a different point in our solar bubble and giving us a second, crucial data point. Right now, Voyager 1 is over 15 billion miles away, hurtling along at 38,000 miles per hour. This was a monumental achievement, marking the first time a human-made object had physically entered the space between the stars, our first tangible step into the larger galaxy. Current limitations of the Voyagers. Here's the fundamental problem. The Voyagers are technological marvels, but they are also relics. They were designed for the powerful environments of planets, not the subtle nuances of interstellar space. Their magnetometers, for example, were built to measure the powerful magnetic fields of gas giants, not the faint, tenuous fields between the stars. Their cosmic ray subsystem can detect energetic particles, but it lacks the sophistication to distinguish between different heavy elements with the precision a modern instrument could, which is critical for understanding the origin of these rays. Furthermore, their power source, which uses heat from decaying plutonium-238, is fading. The initial 470 watts of power has dwindled, losing about 4 watts of electrical power each year. To conserve what little energy remains, engineers on the ground are in a constant race against time, making difficult choices about which instruments to sacrifice next. Their data trickles home to the Deep Space Network at a mere 160 bits per second, meaning it would take over a week to send a single low-resolution photo. The signal is now so faint, billions of times weaker than a watch battery, that it requires the world's most sensitive radio antennas just to hear it. The case for Voyager 3. This is where the idea for a successor, which many call Voyager 3, becomes more than just a dream. While Voyager 3 isn't an official NASA name, it perfectly captures the spirit of a next-generation mission. The actual, formal concept being studied at the Johns Hopkins Applied Physics Laboratory for NASA is called the Interstellar Probe. Led by scientists like Principal Investigator Dr. Elena Provornikova, this would be humanity's first spacecraft specifically designed to explore interstellar space. Its entire purpose would be to journey beyond the sun's influence, born from the questions the Voyagers raised but could not answer. The goal is to build a probe that could operate for a minimum of 50 years and travel at a target speed of over 95,000 miles per hour. This incredible velocity would allow it to reach the heliopause in about 15 years, a journey that took Voyager 1 over 35 years. The mission's target isn't just the edge of the heliosphere, but a destination of 1,000 astronomical units into the truly undisturbed local interstellar medium. This distance is crucial because it's far enough away to be free from the sun's lingering influence, allowing us to sample the pristine material of our galaxy for the first time. Advanced technology capabilities. So what kind of upgrade would a modern interstellar probe get? Let me explain. Compared to the Voyager's 1970s technology, a new probe would be a revolutionary leap. Instead of limited sensors, it would carry a suite of advanced instruments, a plasma spectrometer, energetic particle detectors, magnetometers, and a dust counter, all with at least 100 times the resolution of the Voyager's equipment. Power would come from a next-generation RTG, designed for longevity and providing enough power to run a full suite of instruments for a century. But the real game-changer would be its brain AI-powered autonomous systems. This would allow it to make its own decisions, acting like a true robotic field scientist. It could prioritize data, compressing less important information to save bandwidth for groundbreaking discoveries, and even react to unforeseen events without waiting for the 3-day round-trip communication with Earth. To achieve its speed, the mission would launch on the most powerful rocket available, like NASA's SLS Block 2, and perform a powered Jupiter gravity assist, using both Jupiter's gravity and an onboard engine to achieve velocities previously thought impossible for a long-duration science mission. The interstellar medium mystery. Why is this so critical? Because our entire solar system is hurtling through a cosmic ocean, and we barely know anything about the water. This ocean is the interstellar medium. Our sun's solar wind carves out the heliosphere, which shields us from about 75% of the most energetic galactic cosmic rays. This shield works because the solar wind's outward pressure physically pushes away this deadly radiation. But what is its true shape? For years we thought it was a comet-shaped teardrop. However, models by scientists like Merav Ofer now suggest it might be a sphere or even a deflated croissant. A key unresolved question is how the interstellar magnetic field drapes around our heliosphere, which is crucial for its structure and how it protects us. Our solar system is currently passing through what's known as the local interstellar cloud, a slightly denser region of gas and dust. An interstellar probe could tell us how this local weather directly impacts the shape and strength of our protective bubble. Understanding this interaction is fundamental to understanding our own cosmic environment. Scientific objectives and research goals. Let's get specific. What questions would a mission like the Interstellar Probe finally answer? First, it would explore the unshocked interstellar medium, the pristine galactic material our sun is moving through. This means getting a baseline chemical inventory of our galactic neighborhood, the very stuff from which future stars and planets will form. Second, it would map the structure of our heliosphere in high definition, crossing key boundaries like the termination shock and heliosheath with far more advanced instruments. It would finally solve the mystery of its shape and reveal the physics of its interaction with the galaxy. Finally, the mission would journey to a target of 1,000 astronomical units from the sun. As physicist Ralph McNutt from the APL team emphasizes, getting to this distance would allow us to look back and view our solar system as a complete astrosphere for the first time. From this vantage point, it could even detect the faint extragalactic background light without interference from dust in our solar system, opening a new window for cosmology and studying the universe's first light. It would be a multi-purpose observatory unlike any other. Practical applications for future missions. This isn't just about abstract science, it's about laying the groundwork for humanity's future in space. Let me explain. Any future attempts at sending probes to other star systems will require navigating the interstellar medium. An interstellar probe would act as a pathfinder, creating the first detailed atlas of the space just outside our solar system. It would quantify the radiation risks for future robotic or human missions, which would be impossible without the precise data this probe would gather. At speeds over 90,000 miles per hour, even a tiny grain of interstellar dust can strike with the kinetic energy of a rifle bullet. So the probe would map dust density to inform shielding design for future, even faster craft. Developing the technology to reliably communicate with a probe hundreds of AU away would push our deep space communication capabilities, benefiting all future missions. Furthermore, it would pioneer techniques for autonomous interstellar navigation, a requirement for any craft that travels so far from home that the sun becomes just another bright star. This is essential for concepts like breakthrough starshot, which would need this data to even begin planning. Cultural significance and golden record 2.0. What message would you send to represent all of humanity on a journey that will outlast everyone alive today? In 1977, Carl Sagan's committee assembled the Golden Records. An interstellar probe would carry on this legacy, but a Golden Record 2.0 wouldn't be a physical disc. John Lomberg, the artist who designed the original record's cover, has proposed a digital successor. This new archive could hold petabytes of data, the entire human genome, vast libraries of art and science, and perhaps even messages from the public. The new message would have to reflect our more globalized, digitally connected, and perhaps more self-aware civilization. The very act of creating it forces us to reflect on our collective identity and what we would want to say about ourselves to the cosmos. How do you represent humanity's flaws alongside its triumphs? Who gets to decide? This probe and its message will travel through the galaxy for millions of years, long after Earth has changed beyond recognition. It serves a dual purpose, a scientific instrument pushing the frontier of knowledge, and a cultural artifact carrying the story of humanity to the stars, a true monument to our civilization. Timing and opportunity. Here's the bottom line: if we want to do this, the clock is ticking. The Voyagers completed their grand tour because of a rare planetary alignment. To achieve the incredible speeds needed for this new mission, the Interstellar Probe would also rely on a gravity assist from Jupiter. The APL study pinpoints an optimal launch window in the early 2030s. The plan is to launch on a powerful rocket like NASA's Space Launch System and then perform an Oberth maneuver, firing its own engine at its closest approach to Jupiter to get the maximum possible boost. Missing this window could mean delaying the mission for another decade or more, waiting for the planets to once again align for such an efficient trajectory. A mission launching in the 2030s needs to be approved and funded years in advance, meaning crucial decisions must be made in the coming years. This is a generational opportunity, a symbolic passing of the torch to ensure humanity's boldest journey of exploration continues. It requires foresight and a commitment to science that looks beyond immediate returns, a gift to the future. An interstellar probe wouldn't just be repeating the past. It would be a quantum leap forward. It would push deeper, answer fundamental questions about our place in the cosmos, and test the technologies needed for future missions to the stars. The first Voyagers were our first messengers to the galaxy, carrying a hopeful greeting from a small distant world. This new probe could be our new voice, our new eyes, and our first true step beyond the sun's embrace. Are we ready to take that step? Don't forget to like, subscribe, and hit the bell icon. Thank you for watching InnoVision Tech.